Okay, let's do those ones. So we're going to do 0 degrees, 90 degrees, 180, 270, 360. Okay. What other degrees can we fill in pretty easily? Okay, so we've got the 30. This is backwards 30. So up 30 degrees, backwards 30 degrees. What else do we have? We've got forward 30 degrees, so that's 120. We got backwards 30 degrees, so that's 150. And forwards 30 degrees is 210. Backwards 30 degrees is 240. Okay. Forwards 30 degrees, 300. Backwards 30 degrees, 330. Okay. Okay, this is 45. What is this? 135. Okay. 225. 315. Okay, so we've got the degrees filled in. What do we want to fill in next? The what? The X and Y's. So the ones on the quadrants are easy, right? Because it's a radius of 1, a radius of 1, a radius of 1, a radius of 1. So what would this point be? 1, 0, to the right 1, up or down 0, okay? What would this one be? 0, 1. What would this one be? Negative 1, 0, okay? What would this one be? 0, negative 1, okay. Now, can somebody tell me for the rest of them, what types of fractions do we have? Square root 3 over 2, 1/2, and square root 2 over 2. Okay. Now this one I could even write square root 1 over 2. I'm not going to write that when I put them in there, but I could write it like this. So square root 1 is smaller than square root 2. That's smaller than square root 3. So if we're putting these numbers in order from smallest to biggest, square root 3 over 2 is going to be the biggest number. Square root 1 over 2 is going to be the smallest number. Root 2 over 2 is the medium number. Does that make sense? Smallest to biggest? Okay. So this is how I've memorized my points. Is I think about how far over and up I'm going to go. So this is the middle one, and so it goes in the middle. It goes over the same amount as it goes up, because the root 2 over 2, that's the pair where the x-coordinate and the y-coordinate are the same. Do you guys remember that from yesterday? The root 2 over 2, those were the coordinates that were the exact same. So for this one, I go right root 2 over 2, up root 2 over 2. So the middle points are going to be easy. To the right root 2 over 2, up root 2 over 2. And then the middle one over here is going to be left root 2 over 2, up root 2 over 2. And then the middle one over here is going to be left root 2 over 2, down root 2 over 2. And then right root 2 over 2, down root 2 over 2. And then for the other ones, we have the smallest number and the biggest number. So when we think about the x and the y coordinate, we just have to think, do we go a big distance or a little distance? So for this point, we go to the right a big distance, up a little distance. To the right a big distance, up a little distance. So what's the x coordinate? What's the y coordinate? Right a big distance, up a little distance. Does that make sense? Now this one would be right a little distance, up a big distance. So what would I write for this one? Right a little distance, up a big distance. 1/2 root 3 over 2. Okay, let's do this one down here. This one is left a little distance, down a big distance. Left a little distance, down a big distance. Okay, what if we did this one? This one is right a big distance, down a little distance. Right a big distance, down a little distance. Root 3 over 2, right a big distance, down a little distance. Does that make sense? Okay, so see if you can fill in the rest of those. So think of your big distances, your little distances. Big distance, little distance. Okay, so I'm going to zoom in on each quadrant just so you can double check yours and make sure that your points are good. So here's our first quadrant. Just double check your points, make sure they're good. We all good on the first quadrant? Yes? Okay. Here's our second quadrant. Just double check, make sure they're good. Your x coordinate should be negative, your y coordinate should be positive. We're all good? Yes? Okay. Here's our third quadrant. X and y coordinates should be negative. Both of them. We're good on those? Okay. And then we've got our fourth quadrant. X coordinate is positive. Y coordinate is negative. We're good? Okay, so we're ready for our radians, which is our fractions, right? So can somebody remember what the radians are for 0 and for 180 degrees? 0 and pi, okay? 0 and pi, so what fraction am I going to put up here? Pi over 2. Okay, so we're going to count by halves. I'm going to have 0, pi halves, so that's 1/2, 2 halves, what's down here? 3 halves, and then over here is 4 halves, which is 2 pi. Okay? Now, if I take this and I break it up so I'm counting here, 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 and here, what am I counting by? Fourths, okay? So I'm going to do 1/4, 2/4, which is 1/2. What is this? 3/4. What is this? 4/4, which is 1. What is this? 5/4. What is this? 6/4, which is 3/2. What's this? 7/4. What is this? 8/4, which is 2. Okay. And then do you guys remember what fraction we count for the rest of them? We count in sixths. Okay, so what's this one? 1/6. Okay, this is 2/6, which is 1/3. This is 3/6, which is the same as 1/2. This is 4/6, which is 2/3. This is 5/6. Okay, this is 6/6. This is 7/6. Okay, this is 8/6, which is 4/3. Okay, this is 9/6, which is 3/2. This is 10/6, which is 5/3. And this is 11/6. Okay. Okay. So one thing that you might notice that is kind of interesting is that we've got 6/4, 1/3, halves, 1/3, 4/, 6. Do you see that? And then 6/4, 1/3, halves, 1/3, 4/, 6. So the 6 are always closest to the x-axis, and the 1/3s are always closest to the y-axis. That's something that I can't zoom out anymore. That's something that can kind of help you remember this if you don't want to count the fractions every time. So that can be beneficial. Okay. Do we feel like that was a little bit easier than yesterday was? Guess what we're going to do tomorrow? No. We're going to fill this in again. All right, bring up your unit circles. Or have nose goes. Nose goes, have somebody bring them up. Bring them up, and you're going to place them on this. We're going to make a pile right here. Place them on that. Okay, so we're just going to spot check a couple of these. So if you were doing problem number 4 said 405 degrees. How could you find a positive coterminal angle and a negative coterminal angle for 405 degrees? Okay, plus 360. So 765 is a positive coterminal angle. Subtract 360, that is still a positive coterminal angle because it's positive. So subtract again. Okay, so these are two positive coterminal angles. Those would both work for positive coterminal angles. A negative coterminal angle would be negative 315. So it doesn't mean just that you subtract it, it means that the answer is actually negative. Okay, does that make sense? Okay, do you have to have the perfect right answer to get credit for the assignment? No, you don't. So if you turn this in with some wrong answers, that's not a big deal. Okay, so now you're going to be like, when we do 15/4, now some of us are maybe going to not have right answers for this. So if we had a radian measure of 15/4, I'm going to type this in as a fraction so it's easier to do. So 15/4 is our starting radian measure, and if I wanted to find a positive coterminal angle, what would I do? I would add a whole circle. So 23 pi-4 is a good positive coterminal angle. How could I find a negative coterminal angle? Subtract 2, probably multiple times, yeah. So if I do subtract 2, that's another positive coterminal angle. 7 pi-4 is still positive. going to have to subtract 2 again. So negative pi fourths is actually a negative coterminal angle. Okay. Are there any problems on here that you want me to go over? I wanted to go over those because I knew those would be possibly sources of confusion. Nope. Okay, we're going to get out a sheet of paper because we're going to do the other part of the instructions, which was to graph the oriented angle in the standard position. And I didn't have you guys do that last night because we didn't really, some people might have understood it, but I didn't want you guys to feel confused. So when we do this part of the instructions, the graphing in the standard position, we're going to be graphing the original angle, not the coterminal angles. So graphing in standard position, we're going to go back and we're going to do the 20 problems. So a 330 degree angle, if I go back and look at it, 330 degrees is almost a full circle. So to graph that in standard position, that just means that you start at the positive x-axis and then you go around the circle counterclockwise because that's how the angles are measured. So 0, positive 30, positive 45, positive 60. So we start here at 0 and we go this way around the circle, and that's standard position. That's how the angles are measured. So if I'm going to do a 330 degree angle, I'm going to start at 0 and go all the way around to 330 degrees, and that's how I would draw my angle. So I'm going to say that a 330 degree angle is approximately like this. It doesn't have to be perfect. Mine might be a little bit closer to 315 degrees if we're going to be honest, but that's about right. Okay. Negative 135 degree angle. So there's different strategies mentally. If you've done this, you guys already know what the positive coterminal angle is and the negative coterminal angle is, so that can kind of help you think about where to look on the unit circle. But a lot of times if I see an angle that I need to draw and I know that the angle I'm drawing is negative 135, I look and I say, well, positive 135 is up here, so I'm just going to go that far, but I'm going to measure it in the negative direction. So instead of going up to 135, I'm going to go down that same amount. So I'm going to go down to this right here. And I bet you found out that the positive coterminal angle was 225. Is that what you guys found? Yep. So we're going to measure backwards because this is a negative angle, and we're going to go back 135 degrees, which is in the same spot as 225, but since I measured it backwards, it's negative 135 degrees if we measure it in standard position. So positive angles go up and counterclockwise, negative angles go backwards and they go clockwise. Okay, let's look at number 3. Number 3 is 120 degrees. So 120 degrees right there, just a little bit past 90. So that one is pretty simple. There's 120 degrees. The real reason I did number 3 is because I wanted to get to number 4. So if we're going to graph number 4, this is a 405 degree angle. How do you guys think that I should draw a 405 degree angle? Yeah, first we're going to do 360. We're going to go a full circle to get to 360. We're going to draw, it's going to look a little bit like a swirly. Yeah, so we're going to draw 360, right? We draw the whole circle, and then we know that the coterminal angle is 45 degrees. So we know that 405 is in the same spot as 45 degrees. It's just an extra circle more than 45 degrees. Does that make sense? So I know it's going to end in the same position that 45 degrees would be in. So I'm going to go halfway between 0 and 90. That's where I'm going to stop. So a 405 degree angle would go all the way around the circle, and then it would go to 45 degrees because those are coterminal angles. They're in the same spot. They don't measure the same amount because 405 is a whole circle extra, but they would be in the same spot. Does that make sense? Okay. All right, so what we're going to do is I'm going to give you guys some time, and you're going to go ahead and draw the specific angle that's given in the problem, and you can use the coterminal angles to help you draw it, but the one that you're drawing is the one that's actually printed on the paper. Sound good? Yes, Ms. Rice? Perfect. Okay, let me know if you need some help drawing those angles. So let's look at number 7. Number 7 said negative 11 pi thirds. If you did negative 11 pi thirds and you were looking for a coterminal angle, so doing for your homework last night, if you add 2, negative 5 thirds, add 2 again, 1 pi third is the first positive coterminal angle that you get, and that is important because it kind of tells you where your drawing is going to end up. So anytime you have these drawings where you have to go around the circle multiple times, it's really good to know which radian measure on the unit circle, like which one is actually written on the unit circle, because that's going to help you figure out where to stop. So if we think in terms of our fractions, how many thirds make 1? 3, okay? So from 0 to pi would be 3 thirds. So half of a circle is 3 thirds. So if I'm counting backwards, I'm going to say this is negative 3 thirds, and then this would be negative 6 thirds. Does that make sense? Negative 3 thirds, negative 6 thirds. Okay, so if I start drawing, because I'm going to go in the backwards direction since it's negative, I'm going to do negative 3 thirds, negative 6 thirds. If I do another half circle, how far do I get? Negative 9 thirds. Okay, now I'm going to stop counting by threes because if I were to do it again, I'd get to negative 12 thirds. That's too far. Okay, so I'm at negative 9 thirds over here. Now I'm going to count by 1/3 at a time. So negative 9 thirds, negative 10 thirds. This is the next one that has a third on it. Negative 10 thirds, negative 11 thirds. This is important because if you look, pi third was our coterminal angle that was on the unit circle, and we are ending up at pi third. Does that make sense? So that's always going to happen. Whatever coterminal angle you had that was a unit circle measurement, that's where you're going to end up. That's how coterminal angles work. Okay, so I'm going to keep going. And then pi thirds was my unit circle coterminal angle. That's where I stop. Okay. The same thing is going to be true for number 19. We found that 7 pi fourths was our coterminal angle that was on the unit circle. So we are graphing 15 pi fourths. That's what we're actually graphing. But 7 pi fourths was the coterminal angle that's on the unit circle. So I know I'm going to end up over here. Before I even get started, I know I'm going to stop here. I just have to count how many times I go around. I'm going in the positive direction for number 19. So I'm going to go 4 fourths, 8 fourths, 12 fourths, and then I have 13, 14, 15 fourths, and I end up over here. Does that make sense? So 4 fourths, 8 fourths, 12 fourths, and then 13, 14, 15 fourths, and I end up over here. So I'm always going to stop on whatever coterminal angle I had that was in the unit circle. I know where I'm going to stop, I just have to figure out how many times I go around the unit circle to get there. Okay. The next thing that we're going to do is what is next on the sheet. It says convert the angles back and forth between degrees and radians. And so that's what we're going to do next. We're going to take our unit circle, we're going to flip it over because we're going to kind of use this first unit circle that we did. We're going to kind of use this as a cheat sheet. So this unit circle has how do you find coterminal angles. This is also going to have how to convert back and forth between radians and degrees. So I'm going to say on the front side, I'm going to say just converting. And we're going to do the examples on the back, but we'll go ahead and write the formulas on the front. So converting. The two formulas are to either use pi over 180 degrees or to use 180 degrees over pi. So 180 degrees and pi are considered to be equivalent. They're the same measurement, they're just in two different units. One's in the units of radians, one's in the unit of degrees. And you can see that they're equivalent because if we look on the unit circle, pi and 180 degrees, those are in the same spot. So they're equivalent measurements. Okay, so what we're going to do is now we're going to flip this over. We're going to do some examples on the back. So here we're going to convert from degrees to radians. And we're going to start with 330 degrees. And we're going to multiply it by a fraction. So a lot of times when we have a number in math and we want to convert it into something else or switch the notation or something, we multiply it by a fraction. And we're always allowed to multiply something by a fraction as long as that fraction is the same thing on the top and the bottom. Because if it's the same thing on the top and the bottom, you're multiplying it by 1, which means you're changing what it looks like, but you're not changing what it represents. So that's what we're going to do is we're going to multiply it by something that is the same on the top and the bottom, which is going to change what it looks like, but it's not going to change what it represents. So these are both the same on the top and the bottom. They look different, but they're technically the same on the top and the bottom because they both represent the same measurement, okay? So what we want to do is we want to multiply this by one of those two fractions that has a degree bubble on the bottom because we want the bubbles to cancel so that this will no longer be in terms of degrees, but the bubbles will be gone, and so this will be in terms of radians. That's our goal, okay? So which of the two fractions are we going to use, the first or second? The first one, because it had the bubble on the bottom, okay? So we're going to multiply this by pi over 180 degrees. So the bubbles cancel. Whenever I do this conversion, I'm not going to type the pi into the calculator because if I type the pi in, it's going to give me a crazy decimal, and then I'm not going to have a fraction. And we know that in radians, they're typically a fraction with a pi on top. Okay, so what I'm going to type in my calculator is I'm going to type 330 over 180. You can type it as a fraction if you want, or you can type 330 divided by 180 and then take your answer and turn it into a fraction. Okay, either way you do it is fine. So alpha y equals 330 over 180. I'm going to take that, stick the pi on top. So this is 11 pi over 6. And if you look at your unit circle, you should notice that 330 degrees is 11 pi over 6. Same spot. Okay, the next one we're going to do it with is 120 degrees. So again, we're going to multiply by pi over 180. The bubbles cancel. So I'm going to type in 120 over 180. My fraction is 2/3. So I get 2 pi thirds. Last, we're going to do 405. So I'm going to multiply that by pi over 180 degrees. My bubbles cancel. I'm going to type in 405 over 180. My fraction is 9/4, so I get 9 pi fourths. Okay. Does that make sense for converting into radians? Okay. Now, if we're going to convert from radians into degrees, we're going to want to take the radian measure. So for this one, we're going to do 5 pi over 6. I want to choose a fraction that is going to cancel out the pi, and it's going to introduce a bubble. So I'm going to do the opposite version. I'm going to do the one that has a pi on the bottom and a bubble on the top. I want to introduce the bubble, and I want to cancel out the pi. So this one, I'm going to cancel the pi, introduce the bubble. Now this one, I'm not as worried about decimal answers. Typically, if you're going to have a degree, you're not ever going to write that degree measurement as a fraction. Even if it could have been a fraction answer, you would want that to be written as a decimal. I'd rather have like 157.8 degrees than I would have that be like an improper fraction. So with this one, I'm probably not going to type this as a fraction because that's going to slow me down. I'm probably just going to type 5 divided by 6 times 180. That's going to be the quickest way to type these. So 5, 6 times 180 is 150 degrees. But if you want to type 5, 6 as a fraction times 180, that's fine. You'll still get it right. All right, the next one I want us to convert is negative 11 pi thirds. So we're going to do that times 180 over pi. Our pi's cancel. And we have negative 11 thirds times 180, negative 660. And then let's do 5 pi fourths. Okay, so on the worksheet at this point, you guys can finish the worksheet because we're just going to do these two sections. You can scribble out 37 through 41. We're not going to do that one. But these two are just taking the degree measure or the radian measure and converting it into the other form. And you guys can go ahead and work on that. And then once you're done with that, you can turn them in. And then we'll work on the last little bit of the unit circle stuff today. So on the back of your unit circle, we are going to write SOHCAHTOA. Does that sound familiar? There is, but I don't want to get there yet. So on the back of your unit circle, SOHCAHTOA.
That's how I learned it.
Yeah.
Some old hippie caught another hippie tripping on acid. Yes.
Okay.
Cosine.
Yeah, sine, cosine, tangent. So if this is the angle that we're talking about, then we have the side that is opposite of the angle. We have the side that is adjacent to the angle. Adjacent means next to, the side that's right next to the angle. And then the hypotenuse is always the longest side, it is always the side that the right angle points to. So right here we got the right angle and it's pointing to the hypotenuse. So the opposite is across from the angle, adjacent is right next to the angle, and the hypotenuse is always the longest side. And then SOHCAHTOA means that sine of the angle is the opposite side divided by the hypotenuse. It's just a ratio of the two sides. Cosine of the angle is the adjacent side divided by the hypotenuse. And tangent of the angle is the opposite side over the adjacent side. Does that ring a bell? Does that sound familiar?
Yeah, very.
Yes. Does that sound like comfortable or does that sound intimidating? What feelings does that bring up? Comfortable? We don't like triangles? How about anybody else? What does that make you think of? Just whatever? Yeah. Okay. Okay, so if I drew a triangle like this, I'm going to give you, this is called a Pythagorean triple. It's just a normal set of sides for a right triangle. 3, 4, and 5. If I gave you these three sides, yep, 3, 4, and 5, they're very standard. If I asked for sine of theta, what would you tell me the ratio was for sine of theta? 3 over 5. You'd say opposite over hypotenuse. So you'd say 3 over 5. Okay? What would you say for cos theta? 4 over 5. You'd say adjacent over hypotenuse. You'd say 4 over 5. Okay? What would you say for tan theta? You'd say opposite over adjacent. You'd say 3 over 4. Okay. Any discomfort with any of that so far? No? That's reasonable. Okay. What I'm going to have you guys do is I'm going to have you get out these notes. We're going to finish up one little part of these notes. So if you look right here, you can kind of see that there's a circle on the other side of the page. I should have printed one here, but I didn't. But if you want, you can kind of trace that circle, or else you can just do your best drawing of a circle. Ooh, I did a terrible job tracing that. That's kind of okay. Yeah, so what we're going to do, if you guys remember the notes from yesterday, we kept repeatedly drawing in the circle, we kept repeatedly drawing a triangle. And that's what I want you to do is we're just going to draw a line from the center to the edge, and we're going to drop a line down, and we're going to make a triangle right here. And this is still part of the unit circle, so it's going to have a radius of 1. And if we were to create an x and a y coordinate based on that point, the x coordinate would be this length of the triangle, and the y coordinate would be this length of the triangle. And this was the angle that I measured each time, so I'm going to put the theta right there. So if I was to write the names of all of these sides in comparison to theta, I would say that y is the opposite side because it's across from theta. I would say that x is the adjacent side because it's right next to the theta. And I would say that the radius is the hypotenuse because it's across from the right angle. Are we comfortable with all of that so far? Okay. So with all of those labels in there, if we remember SOHCAHTOA, sine is opposite over hypotenuse. So if I write down the sides for opposite over hypotenuse, I would get y over r, y over the radius is 1, and y divided by 1 is y. So in the unit circle, sine of the angle is just the y coordinate on the unit circle. Okay? Cos of theta is adjacent over hypotenuse. So adjacent over hypotenuse would be x over a length of 1. X divided by 1 is x. And so cos of the angle measurement is just the x-coordinate. So in the unit circle, the x-coordinate is cos of the angle. The y-coordinate is sine of the angle. And that is a huge idea in trigonometry. And it's something we're going to work with tomorrow. Okay, that's going to be the big idea of tomorrow. So I'm going to take my unit circle. And somewhere I have space, maybe up here, I'm going to write cos theta, comma, sine theta. And just remember that cos corresponds to my x-coordinate, sine corresponds to my y-coordinate. That's a big idea in trig. That's something that we care a lot about, and I'll show you how to work with that tomorrow. Okay? Tan is opposite over adjacent. The opposite is the y-coordinate. The adjacent is the x-coordinate. So tan is y divided by x. I'm going to write that down. That's a big idea. Tan of the angle is y divided by x. And if y is sine and x is cos, that means that if tan is y divided by x, then tan is actually sine divided by cos. This is another big idea in trig. It's a big deal. So tan is y divided by x. It's the y-coordinate over the x-coordinate. It is also sine divided by cos. It's a big deal. Okay. So, go ahead and grab your calculators. I'm going to show you how this works. In our calculators, we're going to hit second plus 712, second plus 712. And what we're doing right now is by hitting second plus 712, we're getting our calculator back into the default mode. And if you hit the mode button, that means that all of us should be back into radians now, because radians are the default. So if I was to click cos of an angle, cos of pi fourths, the calculator would spit out the decimal for root 2 over 2. That's the x-coordinate, because it's cos. So if I type in the cos button, the 3 buttons for trig are right here. If I hit the cos button, and then typed in pi, which is right here in blue, second, and then this button, pi divided by 4, it's going to give me the x-coordinate of that point. Root 2, I can verify this, root 2 over 2. It's going to give me the x-coordinate of that point. If I type in cos of pi divided by 6, it's going to give me the x-coordinate of this point. Root 3 over 2. If I type in cos of pi halves, it's going to give me 0. That's how it works. Okay? If I were to do any of those points but with sine, then it's going to give me the y coordinate instead of the x coordinate. Does that make sense? Okay. We're going to practice more tomorrow, but that's the big idea that we're finishing.